Everyone, Jason Turley here, back with more Ethernaut CTF challenges, and today I'll be going over my solution, my walkthrough for the level called King, where it's kind of like a King of the Hill kind of a challenge where multiple users can send money to this contract, to this protocol, and whoever sends the most money becomes the current king, and they can get dethroned or knocked off by anyone else who happens to send more money. And there is a catch. There is a special privileged owner who can just reclaim kingship whenever they want, essentially. So if we look at the description more formally, it does say the contract below represents a very simple game. Whoever sends it an amount of ether, we can just think of that as like money. This is all simulated in our local environment. So this is kind of like Monopoly money. You can substitute ether in your head for dollars or pesos or whatever currency you're familiar with. So whoever sends the most amount of money that is larger than the current prize becomes the new king. On such an event, the overthrown king gets paid the new prize, making a bit of ether in the process. So when we send a larger prize, we will become the new king. However, the money we send does go to the previous king. Your goal is to break this. When you submit the instance back to the level is going to reclaim kingship. So after we're done becoming king or sending money, whenever we're finished and through, the level owner will become the king at the very end. So we need to find a way to stop that from happening. So if we scroll down, the contract, the source code for this isn't very large. There's only I guess, two functions and a constructor. So we can see here, starting at the very top, some of these storage variables. There's an address to store who the current king is. We have two public storage variables here, a prize and another address for the owner. And if we scroll down here inside the constructor is payable, meaning we can send money to and from it. The owner is being set as the person who deploys the contract, and the king is also the person who deploys the contract initially, and the prize is whatever funds they send initially. So if Susie deploys this contract and they send 1 ether to it, then they are the current king and they are the owner, and the current prize is 1 ether. So if we can send 2 ether, or anything more than 1 ether, really, we become the new king. So we can see here the receive function. Receive function is called when you send money to a contract. It's essentially the logic of what should I do once I receive the funds. So here we see a require statement. It's very similar to an assert statement. So whatever value we send, it must be greater than or equal to the current prize. Or the person who sends money or calls this function should be the owner. If either of those two things are true, send the current value to the current king and then update these two things. So if Susie is the current king and then Nakar calls the function with more money, with like $2 or 2 ether, this will pass. Our 2 ether will be sent to Susie, the previous king, and then now Nakar's the king. I don't know where those names came from. Forgive me, guys. I should just use Alice and Bob or whatever. So essentially, that is the main logic of this contract. We can send more money and become the new king. There's no way to change the owner, so that's like kind of peculiar. So no matter what we do, the owner can simply call this function, even if they send no money whatsoever, and they will become the king again, right? Because message.sender is the person who is calling the contract at the time. They're the person who sends the transaction, and the owner will always get the upper hand. So there has to be some way around this. And then lastly, we have this function _king. It's a view function, so it doesn't really do any writing. All it does is reading, and it just reads whoever the current king is and returns it. So this was a head scratcher for me for a good while. I wasn't sure how to circumvent this. I was going down some rabbit holes logically. I'm like, is there some way we can change the owner variable and make ourselves the owner? But there's really nothing going on in this contract. There's no change owner or set owner function that we can utilize. So I looked up the transfer function. I wanted to better educate myself on what exactly this is. I know it makes sense reading it backwards instead of forwards. So it's saying whatever the current value is, transfer that to the king. But what else is going on underneath the hood for this? So I looked up in the Solidity documentation. So here in the current Solidity documentation, this is for, let me hide myself real quick. This is for 0.8.29, but this still takes place and holds true for the current version of the Ethernaut challenge, anything greater than 0.8.0. So we can utilize these docs. So here in the Solidity documentation, underneath the members of addresses section, we can see that the transfer function is being talked about. So if we scroll down a little bit, we do see this note. So if we look at this code example, it's saying x.transfer10. So transfer 10 to the address x, whoever that may be. So if x is a contract address, its code, more specifically, its receive ether function, if present, or otherwise its fallback function, will be executed together with the transfer call. This is a feature of the ethereal virtual machine, the EVM, and cannot be prevented. If that execution runs out of gas or fails in any way, the ether transfer will be reverted and the current contract will stop with an exception. Interesting. So if this is your first time interacting with the Ethereum virtual machine, a lot of this terminology might make no sense at all to you. So let's actually try to break this down. So starting at the beginning, so a contract address. We went over this briefly in a different video, but in Ethereum, there's two kinds of addresses. There are the addresses of a user, essentially. So if you have a MetaMask wallet or a Coinbase wallet, you are given an address with a private key. And that's your way to sign transactions and send it and receive money and do things on the Ethereum blockchain. When we're doing these Ethernaut challenges and we look at the test suite, we do usually see a player called the EOA address, the externally owned account address. So that's us. That's the player. That's the user. That is our wallet, essentially. The other kind of address is a contract address. So the smart contracts, the source code we've been looking at, those exist on the Ethereum blockchain, and those have addresses as well that we can interact with. And it allows us to call functions and read storage variables and things like that. And then as we saw in one of these challenges, I think it was the fallback. I don't remember which challenge it was, but we did see there's two ways for a contract to receive money. They can specifically implement a receive function or a fallback function, and we can read up on those more if we want more in-depth information. But essentially all we need to know is either fallback or receive or keywords in Solidity, and you can implement either one of those to handle receiving money, receiving funds. So when we call transfer on a smart contract address, it will call fallback or receive. So this is a feature of the EVM, the Ethereum virtual machine. And it's saying if that execution fails or if it runs out of gas, gas is essentially just a fee, a transaction fee. So if it fails for any reason, the ether transfer will be reverted. So a revert is essentially just an undo. So how can we utilize this, right? At the very end, we know that the current owner will call this function. They will send some ether, or even if they don't send anything, even if they send a value of 0. At the very end, the owner will call this function, they'll trigger this code, and they will be the king again. However, if we can get that to revert, then it will undo their transaction, and we will stay the king. So there's a few things we need to do. So let's actually open up some code and kind of start writing a proof of concept. So once again, I'm using the Ethernaut X Foundry GitHub repo that has all of the Ethernaut challenges ported over to Foundry, which is a modern Solidity smart contract testing framework. So I have the contract here. I did add some notes that I wanted to go over. This is a link to that note on the transfer function that we saw earlier. And I'll leave this in the description down below if you guys want to read up on it further. And we see there have been some comments added. The message.sender has been just marked as payable. So we know we need to do a few things. So let's open up a new file. We have a few goals we want to do. First, we want to become the king. And then we want to cause the owner's transaction to fail. And let's save this. We'll call it kinghack.sol, and we'll save that right here in the same source directory as king.sol and kingfactory.sol. So these are our goals for this contract, for this attack vector, essentially. So let's make sure everyone can see. Every contract will need this SPDX license identifier. We'll just use MIT and Pragma, Solidity. Let's use any version greater than 8.10. Contract King Hack. And I'll move these comments down here. And we also need to import the regular king contract. So king.sol, let's import that. We will need a constructor that gets called when we initially create this contract, and let's give it a handle to the king. So we'll just call this target, king_target, and target equals _target. All right, let's handle this first case. We want to become the current king. So let's just create a function. I'm not very creative with names, so I'll just call it become king, and let's mark it as external so we can actually call it from outside. And I think it will need to be payable, maybe not. We'll see if that was an unnecessary modifier. So how can we become the king? We can become the king if we send more than the current prize variable, right? So if the prize is currently set to 1 ether, if we send that amount or greater, then we will become the new king. If we scroll up here, we see that the prize variable, it is global and it is public, so we can read it. We don't need to send more. We can send the same exact value if we really wanted. So let's actually do that. I'll say uint 256 amount equals target.prize. And I do need parentheses because I am calling essentially the getter function here. We don't want an underscore here. We just want that. And maybe calling this target's confusing. Maybe I should call it victim or just underscore king, but I'll just leave it as target for now. I've never been really good at naming variables. So we know how much we want to send. I'll just add a 1 to it, like a 1 ether. Why not? And now we need to actually send this to the target contract. So the syntax for this will be a little ugly. We need to typecast our contract to an address, and then we need to do a .call. In these curly braces, we have to write the word value to set message.value to our amount. And then we have these parentheses with just blank quotations in them. So we are calling the king address, our target address, the target smart contract, and we are sending ether to it. So whatever the current price is, just add 1 ether to it and send that to the contract. There's a few ways to send money to a smart contract. We could also, as we saw here, do a .transfer, and there is also a .send. But it is recommended to just do .call because it saves on transaction fees, but that's way out the scope of this video. And it is giving us an ugly yellow compiler warning. It's saying, hey, you're not actually using the return value of this, but this should be fine for our very simple contract. And then our next goal is cause the owner's transaction to fail. In order for that to happen, we do want to implement a receive or a fallback function. So we're going to implement a fallback function, external payable. And if you're not sure what the proper keywords or visibility you should add to this, if you just take these out, you will get this red squiggly. You will get this compiler error. It's saying no visibility specified. Did you intend to add external? Fallback function must be defined as external. So that's very helpful. If we mark it as public, it'll still give us this same error, and it's saying it must be marked as external. So you can use the compiler errors to kind of help guide your code. So essentially, we want this transaction to fail. We want it to revert. This only gets called when the owner at the very end tries to regain the throne, and they call that receive function, and it will trigger our smart contract, and it will trigger our fallback. So we can be explicit here and call revert, which will tell the owner's transaction essentially to fail, or we can leave this blank. We'll try both ways. Let's try to explicitly call it revert. And I think I can actually put a message in here. I can say something like transaction failed. Please subscribe. And let's see if this actually works. So we'll come over here to our test case, and we need to run this. So let's do create our king hack. King hack equals new king hack. And then we need to throw in the handle to the king smart contract. So we can say king hack dot become king. And is that it? Is that the only thing we need to do? So we become the king. We send our transaction here. We are the EOA address. I guess we could throw in an assert equal EOA address equals Ethernaut king. Let's see if this actually even works. So I will do a forge test. Forge test tac mt test. What's this level called? King hack. And we do get a fail. So we did implement something incorrectly. Let's hit the up arrow and do attack V. So we're going to do 3 V's here just to get more verbose output. And oh, this is my own assertion that fails. We don't really need that. Okay, here we go. So we try sending, so we call become king. So this is the function we created, right? We call become king. It grabs the current prize value, which is 1 ether. We add 1 ether to that, so 2. So we call receive. So our message.value is 2. 1 plus 1 is 2. So this makes sense. We're hitting the receive function inside the king smart contract, and we're getting this error out of funds. So our smart contract, kinghack.sol, has no money in it. By default, smart contracts don't have any money in it. So if we come up here, we see our EOA address. This is like our player address, or our wallet is being dealt 5 ether. So our user has ether, but the king hack contract does not. So we could call a vm.deal that way, or what's better is instead we can use this ugly syntax and say value to ether. So when our user calls this become king function, we are sending our ether to it. And let me actually edit this. Instead of this being amount, let's just hard code this as message.value. And over here, we'll say uint 256 amount equals Ethernaut king dot prize plus 1 ether. And then down here, we will send the amount. So that looks good to me. I could probably add comments to this to make it a little easier to read. We don't really need this assert statement, but for the time being, let's leave it. Let's clear our screen and let's rerun this. And this time we see that everything did pass. We are getting an error here in our assert. So the king isn't our EOA address. The king is the King Factory address, I think. Oh well. We passed the level. We don't need this assert equal. That's just something I was trying to add to be cute. But if I clear this out, and let's just clear the screen and rerun this command, we still pass. And let's scroll up so we can look through the transaction history. So 3 V's will show you the output when it fails, but ours was successful. So if you want to see the call trace, the stack trace of a successful execution, then we need 4 V's. So if we scroll up a little bit, we don't need to go all the way to the top because a lot of this is just the level initialization. We see the King Factory and its address, and it's setting everything up. But if I come down here to the things that we can that we control, we see King prize. This is the storage variable, the global storage variable that we call. So storage variables have getter functions to let you read the value. So we see we're able to read the result of it. The current prize is 1 ether. It looks like a huge number because ether is stored in way. Essentially, all that means is 1 ether is the number 1 with 18 zeros behind it. And we see that right here in this notation. So you'll see this a lot, 1E18. So the number 1 with 18 zeros after it. So this is 1 ether. Then we create our king hack address, our contract, and we see the address it's being created at right here. We're calling the become king function. We're passing in 2 ether to it. It hits the target king contract. It hits its receive function. It sends 2 ether to it, and then we're good. So then they try to submit the level, and we see that the current owner or the level instance tries to reclaim ownership. So we see the king receive function gets hit again. So this is the transaction that the owner is doing. It's trying to steal the throne at the very end, right? So it calls receive. It goes into our attack contract or king hack contract. It hits our custom fallback function, and we explicitly call revert. And look at our cool error message. Transaction failed. Please subscribe. How neat is that, right? We made our own custom error message for a revert. So this is why we passed. When the owner tries to come in and usurp the throne and take it from us, we hard code a revert to cancel their transaction. So let's see what happens if we just comment this out, if we get rid of it, essentially. Will this still work? So I'm going to open up my terminal. I'm going to clear the screen and hit the up arrow again. And it says it fails. So we see here at the very end, we see our ether, we become the king. And then at the very end, in this fallback function, it does not work. They hit our custom made fallback function and it just doesn't do anything. So we do need something there. We do need a revert or some type of logic to cancel this out. I could probably read up on this further in the documentation. I thought there was a way to cancel it out or stop their transaction without a revert statement. Maybe I can be kind of cheeky and do like comment this out. Because I know they're going to try to call it. So maybe I can do like require message that value equals like 100 ether, like something absurd like that. And now we try to rerun it. We see that we do pass. It does work. Because when the owner comes in and they call receive, they do not have enough Ethereum, right? And we could add like a custom message here as well to the require statement. Must send 100 ETH. And we see it fails, and then it prints out our message, must send 100 ETH. So however much Ethereum they sent, it was probably 0, it was probably nothing. It did fail. So there we go. There's a few ways to solve this challenge. It was initially kind of confusing. So I think that is something that makes smart contract security pretty interesting, because addresses can be a contract or they can be an end user. So when you are writing these apps and these protocols, you do need to think about these edge cases of, hey, I could be interacting with a malicious contract, right? It's very different than I think traditional cybersecurity in that sense. And it's just kind of fun, just something to think about. So hopefully you guys found this useful or enjoyable. Please leave some comments down below, like, comment, and subscribe, all that jazz. And as always, guys, take it easy, and I will see you in the next video.